Okay, we're going to start walking through a code to start thinking about optimizing the computational performance. And so really what we're going to do in showing here is we're going to develop some numerical methods, and you can download all of this from the Git site, that just sort of walk through the implementation of these Euler or leapfrog schemes on the one-way wave equation, heat equation, and just show you how it works and how we can optimize performance by essentially making the CFL as large as possible without violating the CFL condition, and that's going to give us the best performance we can, or the fastest solution that we can get out of that. So computational performance, first of all, let's just reevaluate what we're going to do. What we've been looking at quite a bit in previous lectures is time stepping for the one-way wave equation, diffusion equation. In fact, for those, we can explicitly compute the CFL condition that you need about whether things are stable or unstable. And then finally we'll do an example also too of something like this, which is a nonlinear Schrodinger equation where I can't necessarily compute the CFL condition explicitly, but we can still march this forward in time quite nicely. Okay. So first of all, let's set up the structure we want. We're going to need derivative matrices, and remember, this is what they're going to look like here. So it's going to be this matrix here. So a one derivative matrix is going to be zeros on the diagonals, one on the off diagonal, upper off diagonal, minus one on the lower diagonal. I'm also putting here on the boundaries 1 and minus 1, which are periodic boundary conditions. So that's what I'm going to assume for now is periodic boundary conditions. And so this matrix, we're going to have to make it because we're going to use it and exploit it when we do our one-way wave equation solves. The second derivative is for the heat equation, and now it's -2 on the diagonals, and then we have 1 and 1 on the off diagonals, on the upper and lower. 1's on the corners, right? 1 down here, 1 up here. Those corners are, for the periodic boundary conditions that we have. So this is the second derivative matrix with periodic boundary conditions. The previous one was the first derivative with periodic boundary conditions. And that's used either for the one-way wave equation or the heat equation. So we're going to use these in our code, in our setup. Now, a reminder of what we're going after, so for computational performance here. So let's consider the one-way wave equation. What we know is we have an Euler scheme and a leapfrog 2-2 scheme. The leapfrog 2-2 is stable for lambda is less than or equal to 1. And Euler is always unstable. Okay, so that's what we found so far. We actually were able to explicitly compute these things from a von Neumann analysis. And for the heat equation, we are also explicitly able to do the same thing, which is we found for the Euler that CFL being less than or equal to a half is stable, but for the Euler, for the leapfrog 2-2 on the heat equation, it's always unstable. So these two different schemes perform very differently depending upon if you're in diffusive behavior or wave behavior. Okay, so let's start setting this up and programming, and you just start seeing the nature of the instabilities we're going to get. All this code you can download, so just go play around with it. Play around with the schemes. It's got lots of things there. You can make things blow up really nicely if you like, and you can get nice stable solutions as you want too. So it's really easy to play with. It's a very fast code, and oftentimes when it blows up, it does so very quickly. So you're just right away. It's like you can see this thing, the behavior go terribly wrong for you if you violate the CFL condition. And so it's immediate what happens, and you can start seeing the natures of the instabilities that might come up. So here we go. I'm going to start off here. Notice I wanted to bring in here this thing I wanted to highlight here. I'm going to bring in this sparse diagonal matrix structure because that's really what you should be using for those derivative matrices. So as you get bigger and bigger and bigger, you're only saving the non-zero components, which is just a few diagonals on those matrices. Okay, so let's set this thing up. I'm going to decide a time bin here. I'm going to go out to 4. I decide a domain, size 20, number of points, 200 points. I'm going to chop it up. By the way, this is a very important choice right here. When I chop this up, that's going to determine the dx. So whatever I pick L here and N here, that's going to determine the dx, which I compute right here. I'm doing periodic boundary conditions, so I define the domain, just take the first n points. Here's my dx. Okay, here's my dt that I pick, so I'm going to pick a dt when I'm stepping. And here's my CFL. So the dx is determined by that number of points there, and then I can move around my dt. Of course, if you want to solve the solution, get the solution as fast as possible, you like as large a dt as possible, but that's going to make your CFL bigger. And often there's a restriction on the CFL. We know that if you're doing a leapfrog for the one-way wave equation, this CFL better be less than 1. And if you're doing the heat equation for the Euler step, this better be less than 1/2. Okay? I'm going to decide how many time steps, and here's our time counter that we have here. Okay, once I have this, I define, for instance, we're going to do this with leapfrog to start with. So I'm going to solve the one-way wave equation with leapfrog. So for leapfrog, remember, I need 2 time points. Leapfrog, unlike Euler, which I can just pick a time, initial 1 slice of time and march forward, leapfrog requires me having 2 slices of time. So I have the initial condition, and I have the next, and I know that the analytic solution is, so I know what U1 is. Oftentimes, to get the next slice of time, you could use an Euler step, even though it's unstable, for 1 delta t. That's not going to blow up in 1 delta t, so you just approximate the next step, and then you can use those 2 to march to have the 2 lines of time, in other words, for you to march the solution forward. I'm going to keep track of my solution in this matrix here, so I'm going to populate it first of all with a bunch of zeros. I'm going to write in my initial condition, the next time point, and now what I'm going to do is, as I march forward, I'm going to fill this solution matrix up with my approximations to the solution itself. Here's the entire code. Then, okay, first I got to build my derivative matrix, and here it is. So again, SP diags. This is the first derivative matrix, so it's -1 on the off diagonal -1, 1 on the off diagonal 1. So n by n, here's where I put in my periodic boundary conditions. There. All I've done with this is populated this matrix as mostly zeros except for these diagonals. So I put those in, and now I'm ready to march. And here's the entire code. So I'm going to work this through, and this here is my scheme. So this solution at U2, right, which is the future point, depends on 1 time point ago. This is leapfrog, remember? So leapfrog says, my current time point is U1. So I predict U2 by using U0, 1 time point ago, plus the CFL number times A times U1, and A gives me my neighbor contributions. Once I've taken that step, I update U0 and U1, and I save my solution, and I loop through. That's it. That's the entire code. I am now time stepping, evolving into the future, and if this CFL is bigger than 1, it will blow up. If it's less than 1, it will be stable. So let me show you some results. Here is the simulation of that with CFL 0.5. So leapfrog 2.2, this is exactly what the solution is supposed to look like. It's the one-way wave equation because there's a wave going one way. It doesn't change its shape or its form. So we know this is the truth because this is actually, you can write down the analytic solution to this. And this then is a stable solution to this because I've chosen my CFL well below the boundary, which has to be below 1. Okay? So that's the kind of thing you would be looking at there. Now, let's violate the CFL, or let's solve this with an Euler scheme. The Euler scheme is always unstable, and if I have a CFL bigger than 1, it's going to be unstable. And here's these 2 simulations right here. So, this is what you get. In one of these, you have a leapfrog 2.2 with the CFL being 2, and in the other, you're doing an Euler step. And notice, the main thing to notice here is I've stopped the simulation pretty early on, but these solutions here, if you go out a little further, it essentially goes to NANs. Your solutions blow up to infinity. They'll also be 10 to the 30. They'll be massive. So I've stopped it. I've essentially freeze-framed this just when the instability starts so you can see it. And you see, you don't have to go that far out before this thing takes off. Like, this is not that many iterations into the future, and this thing is blowing up, okay, on you. And by the way, initially it looks like some kind of, look at this, waves are being shed from this physics wave. It's all numerical artifact. This is all due to the fact that you have an unstable scheme. So this is violating the instability or coming up with an unstable scheme. You can get very different behavior. And notice that the instability is very different for the Euler versus the leapfrog. So just keep that in mind. It's not like the instability always looks the same. It can be very different in how it looks. Okay, let's. I'm going to solve. If you solve the nonlinear Schrodinger, now you're not necessarily having an explicit representation of the CFL where the stability criteria is. But here's the discretization. And again, you could just make up a scheme to march this forward. Solution in the future, right? Here's your center difference. And here is your nonlinearity, which is now mod u squared u in this thing here. Okay, and that's your time derivative. And then you're just going to set this up into a leapfrog scheme. So what I've developed here is I took this and did a center difference in time, and then you get this here as your leapfrog scheme here. And it's leapfrog 2-2. And the reason I use leapfrog 2-2 on this one is because this in fact has sort of wave behavior dispersion in it. So it would be a more appropriate choice probably to choose leapfrog versus choosing Euler, which we knew on at least the one-way wave equation blew up. So we do a leapfrog here. Almost all the code goes through exactly the same, and this is just now the update rule from what we had here, right? So here's your little code, but this little section of code here, which is the one-way wave equation, just gets traded out for that piece of code right there. That's it. Once you have that, you can simulate it out, and let me just show you. Here's a stable solution, right? So I've taken my delta t small enough that it's stable. I don't have a boundary. I don't know exactly where the CFL condition is to make it stable, but if I take delta t small enough, this will be stable. And if I just keep violating, take my delta t big enough, I start to see the blow up that happens here. This is a violation of the CFL. So even though I don't have an explicit computation of the CFL, you can clearly see stable versus unstable behavior, and all because all I've done essentially is violated the CFL condition on that. So these are really practical, important considerations. When you're thinking about time stepping, it is absolutely critical that you pick a stable scheme. And even if you can't compute the CFL directly, part of what you have to do is called a convergence study. Is you have to pick a delta t, cut it in half, make sure your solution isn't changing as you cut the delta t down. If your solution changes when you cut the delta t in half, that means it's not converged appropriately. Okay. However, once you've got it converged and you feel confident that you have a stable scheme, then you usually can start doing this, because CFL on complex problems, you can't compute explicitly a CFL number. But lots of different schemes I've presented to you. Choose one wisely based upon a CFL condition if you can, or based upon what we know about the characteristics of the physics. If you have wave behavior, you pick leapfrog schemes. If you have diffusion behavior, you pick Euler schemes. If you have both, you might do operator splitting. You've got to be intelligent at how you use schemes. And people have thought long and hard about this for quite a bit of history, decades. And so your best bet is, given a problem, look around in the literature, see what people have come up with as good schemes, because they've done all the things you'd have to do, which is investigate different options until we have something that works really well, that's very accurate, really stable. And so those are the things you always want to consider in optimizing your computational performance.